This is a toy. For just about $20, a kid can enjoy flying a helicopter just like this in their own home. When I was a kid, I grew up playing with small plastic helicopters, only pretending they could fly. But now, within minutes, I can learn and fly this copter for real. What's up, guys? I'm Frank. I'm a senior in computer engineering, and so is my partner James. Unfortunately, James couldn't be here today for filming, so I'll be giving you guys a rundown on our project. James and I are both interested in robotics and love solving challenging problems. So we were thinking, what if we could design a robot, just as if it were a kid, to walk around and fly a helicopter? Well, with just 10 weeks, we set out to create, if possible, what we call a vision-controlled autonomous system, or for short, ViCAS. And who knows, maybe in 20 years, a kid could be playing with a toy similar to our system. Before getting started, we needed to decide on ground and aerial robots. We decided to go with commercial off-the-shelf hardware so we could focus on software algorithms. For the ground vehicle, we got our hands on a TurtleBot, which is based on the Roomba vacuum cleaner and comes with a Microsoft Kinect. For the aerial platform, we purchased a CrazyFly, which is small, indoor-friendly, and has accelerometers and gyroscopes to help with stability and control. In order for the TurtleBot to pilot the CrazyFly, it must first know where the copter is within the room. While the TurtleBot already has a Kinect which can see in 3D, we opted to create a stereo camera. A stereo camera utilizes two cameras, just like our eyes, to view a scene in 3D. Camera calibration finds the separation between cameras, focal lengths, and other camera parameters used to calculate the depth from each pixel. This sensor allows the TurtleBot to see smaller 3D objects, such as our copter, leaving the Kinect to focus on ground-based obstacles and TurtleBot navigation. What you've been seeing is the final result of the tracking algorithm. But first, let's rewind to when the copter is not in the scene. The stereo cam generates 3D data known as a point cloud, in contrast to a single camera producing just a 2D image. To find the copter, we first look through clusters of points to find potential candidates. Clusters in red are defined as being too large or too small to be the copter, while yellow clusters pass the size requirement but do not have the correct shape. Green clusters pass both requirements and are projected into the 2D image to be compared against a trained model to check if they look like the copter. If the candidate passes this final stage, it is determined to be the copter. On the next algorithm iteration, instead of looking through the entire scene, only a small 3D region is considered around the previous copter location. The region grows when the copter is not found to account for any direction the copter may have moved. While the copter is found, the region is locked in, and the copter's 3D center is published to the control code. Before attempting any aerial acrobatics, we wanted to enter the copter into a controlled hover. In other words, hold position at a set 3D point called a target. To do this, we implemented 4 PID control loops. A PID loop works by taking in an actual value, typically from a sensor, and a target value set by the user. From launching the copter to achieving a constant altitude proved most challenging. The PID was being too aggressive and causing the copter to overshoot its target. With the tracking algorithm only publishing the copter's center at around 7 Hz, we tried improving the frequency, hoping the vertical thrust PID would become more responsive. This required a new approach to tracking. A new tracking algorithm was implemented by use of background subtraction. The algorithm determines static portions of the image to be background, as seen in black, and moving portions, indicated in white, to be foreground, and thus potential copter candidates. This works much faster and publishes the 3D location at around 15 Hz. Since the cameras are not moving during copter takeoff, this algorithm is useful to gain control before moving and switching back to the previous, slower algorithm. With background subtraction enabled, the PID loops become more responsive and are able to keep the copter in the frame, but not long enough. Unfortunately, more work needs to be done to make the PID loops more accurate. We expect there could be issues with latency, but are not sure at this time. Overall, the project was a mild success. We created a stereo camera, 2 tracking algorithms, and we controlled the Crazy Fly with PID loops. In spite of not being able to hover the copter, we still created what we call a ViCAS. We may not have been able to control it to the degree we wanted. However, it is still a vision-controlled autonomous system. Thanks for watching.